Hello, it's 9 o'clock here and 1 p.m. in UK. Catherine, are you ready?
I'm ready.
Okay, cool. Hello, good morning and good afternoon and good evening. As always, welcome you to this World River and Delta System Source to Thinker webinar series. And this is Paul Liu from NC State. This webinar series is co-sponsored by NSF, North Carolina State University, Louisiana State University, East China Normal in Shanghai, and Utrecht in Netherlands. And today we are very delighted to invite Dr. Catherine Russell from University of Leicester and Louisiana State University come here talk about Anthropocene Rivers. And that's a very interesting topic. Before I introduce Catherine, as always, this is marked as 107 talks in our whole webinar series. And I think this is one of the very good thing of the pandemic gift giving to us for this community. We have more than 100 talks archived very well on our YouTube channel, also available from Bilibili station. At the same time, we also maintain a Source to Think Twitter account, and we'll announce all related talks and news. You're welcome to follow us on Twitter. So next Wednesday, remember, because this coming weekend, UK and European will change to the daylight saving time. So starting from next week, we shift back to the normal. London will be, UK will be 2 p.m., Paris will be 3 p.m., the talk. So, okay, next Wednesday, Bob Hilton from University of Oxford will come here talk about controls on the emission of the CO2, and particularly the net carbon budget of river catchments. That should be also a very interesting talk. Please mark your calendar next Wednesday. And Beijing time still 9 p.m. And Catherine, as mentioned, Catherine actually is an honorary fellow and postdoc research at the University of Leicester. She originally also graduated from this university 2013 and also get a PhD geology and geophysical geography from University of Leeds. And her main research is to understand how surface processes cross the Earth's systems and how, related particularly in the Anthropocene stage due to the human intervention, and how such adjustments will affect the system's response to further impact on climate change. So, Catherine, we are looking forward to a talk. Now you can share your screen.
Sure thing, thank you. Can you see that?
Yes.
Fantastic, thank you. Okay, cool. So we'll talk today about Anthropocene rivers then. So we're going to go through this from the large scale down to the small scale. And this logo down in the corner here is the Anthropocene Sediment Network, which I'll tell you about at the end. But yeah, so we're going to be going from the big down to the small. So the first thing we need to talk about then is the Anthropocene. So the Anthropocene is a time interval marked by rapid but profound and far-reaching change, which is in a series of events to the Earth's geology, currently driven by various forms of human impact. So the existence of the Anthropocene has sort of been agreed upon. It was voted in the Stratigraphy Commission about 5 years ago, and this year it's going to be decided when it started and where the GSSP is going to be placed. So, the Anthropocene is functionally different to the Holocene, and we're seeing the highest CO2 from the last 3 million years, highest methane for the last 800,000 years, and the highest reactive nitrogen for possibly the last 2.5 billion years. So the place where we're thinking the Anthropocene might be, so this is being currently done by the Anthropocene Working Group, is about the 1950s, and you can see that a lot of these graphs kind of jump up in the 1950s. There was a big change in how things happened then. So we're seeing that everything from McDonald's restaurants to paper consumption towards damming of rivers and population as well, all kind of accelerate at the point of the 1950s. As well as this, there's this, you've got the 1950s drawn on here. We can see that there are far more materials that actually come into wide usage at this point in the 1950s as well. So the diversity of human-made materials on Earth increases at this time too. So when we think about sedimentology then, within that Anthropocene framework, the aim of sedimentology is to derive information about the depositional condition of sediment and how it relates to other sediment as a coherent understanding of the evolution of sedimentary sequences spatially and temporally. And the scientific basis of sedimentology is sort of uniformitarianism. And this doesn't just happen across the temporal scale, sort of like the past to the present. We're also thinking about this in like how we relate one understanding to another situation. So sort of taking the concept of uniformitarianism a little bit more broadly, it's how we take the experiments that we do in the lab and apply them to the wider world, how we take the classic models and apply them. So it's kind of the application of one knowledge to another situation. So when we move into the Anthropocene, comparing it to the Holocene, we find that humans have transformed the global water system, sediment flux of these systems through engineering and climate change. And so many fluvial systems are under stress. And I think in the sourcing archives, Jim Best actually talked about this with large rivers. Impacts include sediment starvation, which can have profound impacts on delta behaviors and associated rates of land subsidence. There's also pollution as well, which I'll talk about in the second part of this talk, but also humans are enacting the largest change to fluvial systems since the evolution of land plants in the Devonian period. So we're going to start by looking at landscapes and then processes, going down in that scale. So a classic model of a meandering river, it's something that we're fairly familiar with, and just a few things I want to point out on here. So the river is able to break through its levee during the flood, and the water will carry the sediment onto the floodplain and naturally build it up so that the floodplain stays in equilibrium with the channel. When a river bend can become too sinuous, the up and downstream limbs will meet up and cause an oxbow lake by natural means. We also find that the natural levee deposits on the side of the rivers can help to sort of mitigate some of that flooding. And also we find that the river is unbound and free to meander across the landscape. Vegetation growth is natural and unrestrained, and species diversity is high. And we find that we've got these scroll bar deposits recording the historic positions of how this meander has migrated and moved over time. And we can end up finding these amazing archives. These are the famous Fisk maps from 1944. I feel like, can't really talk about meandering rivers without showing one of these amazing maps. And you can see the scars across the landscape from this as interpreted by Harold Fisk, showing how diverse and how mobile these systems naturally are. And this is the Mississippi River. So when we think about how we as sedimentologists will approach understanding one of these systems, a natural river system, we look in like the rock record, is this image from the Isle of Wight, from the Wealden Formation shows, or from something like the natural environment that I just showed with the Fisk map. We're looking at the grain sizes, the lithological composition, the clustering grain characteristics, morphologies, the juxtaposition of strata, lateral and vertical variabilities, paleo-flow indicators, and biological influences. So we're just going to sort of go through a few of the changes that humans have enacted, and we'll start to see, the reason for this division and why I'm proposing Anthropocene rivers. So large-scale landscape changes then. So we know that humans have been affecting river systems for many thousands of years, and most rapidly since the Industrial Revolution. But importantly, we need to remember that rivers still have significant agency and will be impacted by future climate change. So we have to understand how these rivers have been changed and what that's going to mean moving into the future. So we have all sorts of things, and this image is from the Giving 2018 paper. So we've got waterway maintenance, bridge building, port infrastructures, agricultural developments, irrigation canals, which both brings in water and also releases pollutants, all sorts of things that occur along these river systems. And then there are many challenges that come with living near a river as well, some of which are natural, some of which are exacerbated by humans. So we've got drought, flooding, littering and pollution. to start with. So you can see the Colorado River has been drying up. So it says 1999, 2013. This is the dam, the reservoir behind the dam along the Colorado River. One of many, I should say. But anyway, you can see there's significantly less water in 2013, as much of this water is diverted towards agricultural endeavors. This is a flood from May 2011 along the Mississippi River, and you can see that this man-made structure here is causing, some of this flooding to perhaps be a little bit more exaggerated than it might have naturally been. But of course, this is really difficult to tell, because once a river gets to a certain point of, management, it can be really hard to tell what it would do naturally. I think in the case of the Mississippi River, it would like to be flowing towards Atchafalaya Bay. So the whole thing's kind of anyone's guess at this stage, I think. But I don't know. Clint's in the discussion, so I'm sure I'll leave that for him. So then we've got surface macrolitter on the Rhone River. So pollution, as I said, I'll be chatting about that a bit later. This is definitely human added. And then we've got the Danube River Basin knowledge transfer as well. So social and political challenges, possibly the most complex and important thing that we need to be considering when we're looking into these Anthropocene landscapes, because of how complex the reasons are behind the necessity for the changes. So when we're looking then at sort of the pluvial responses to the engineering measures, we find that that's actually barely documented. Like, we know the hydrology, we know the way in which the river will specifically behave in this circumstance, or how to manage the high flow and that kind of thing. But we don't always necessarily know what this means long term, and how this is going to actually imprint itself into the geological record. What does this actually mean for the response of the river towards these measures? So human-induced changes to rivers then will, the sediment yield along the Yellow River rapidly increased when farming began, and then decreased again when it became managed. We noticed the sediment yield actually decreased when Fort Randall Dam and Gavin's Point Dam were installed in the 1950s, which then had downstream impacts, including on the building of Belize Delta, which is where New Orleans sits. We find that the cross-section of the river can change shape as well due to human influence. And when we're looking at biostic change to rivers, the Mississippi River will flows through many highly farmed areas. And so we find that pollutants and chemicals that may then end up in the waterway end up in further downstream and become, part of, they affect the ecosystems that are then in the Gulf of Mexico, causing eutrophication, and what we find here is a dead zone. Invasive species is a problem. Things like big head carp, which were introduced into fisheries, around in America, because they eat everything, have been released into the Mississippi River, and they eat everything. And there were schemes to try to stop them getting up to the Great Lakes. And systems that were never connected now are by canals. I think you can go by boat from the Gulf of Mexico up to New York. Pollutants and chemicals affect wildlife, both in rivers and downstream, as you can see from the diagram. And then, of course, we have locks and dams confining ecosystems as well. So in the 1800s, there were no major dams, but there were 60,000 major dams around the world by the present day. And dam distribution in the USA has boomed. And also we're seeing this in many other catchments worldwide, such as the Mekong catchment. And this kind of means that our natural smooth source to sink profile is now quite staggered and stepped. So we have these kind of things, such as, say, we've got 5 free flowing sections along 78 between the 78 barriers along the Danube River, when this was once one large free flowing section. And I'm just sort of approaching this from a sedimentological perspective, like, what does this mean? Like, how are we redistributing some of the materials and the energy and all this kind of thing that we normally talk about within sedimentology because of this new step profile? And these dams can accumulate sediment. This is a fantastic paper by Bruce et al. And you can see that we've got, projections into the future up to 2100, looking at the amount of sediment that is likely to accumulate behind some of these dams and projected proportions. And dams do in fact fill up, such as the Mandalay Dam in Iraq. So if we're looking at the morphology and sedimentology of a dam and reservoir, we can actually find that they may actually have their own sort of sedimentological systems. So when the river inflows, we end up with some sort of delta, perhaps, and then when the water comes out the other side, it's actually coming out rather fast a lot of the time, and actually warmer than it would have done when it came in. So this is going to have effects on ecosystems, and the sediment then that's being accumulated here is no longer in that river system. You can get seasonal fluctuations of reservoir level, which might have implications for how the stratigraphy develops. And the dam itself, in this case, is clay core covered with earth, but an external line of concrete, but there are many, many other ways in which the dam itself can be constructed. So there are lots of ways in which these things, can accumulate sediment. And ultimately, they're sort of a river and sort of a lake. So yeah, this is something that should be out in the next couple of months, actually. So we look at the Mississippi River then. I'm going to sort of look into a little bit of a case study on here. We've already sort of touched on some elements of the Mississippi so far, but we'll just have a quick look at the history. So the timeline of the Mississippi River then, from the time of the dinosaurs all the way up to the present day, it's got a very long geological history. And this includes, going through the Laramide orogeny and the Laurentide ice sheet, and how each of these events has kind of adjusted the catchment and changed the way in which the river is developing. The meandering system was actually only established fairly recently. There have been phases of meandering throughout its history, but the system that we see today is kind of like a sheen on top of a huge history and deep stratigraphy of a very complex and deep network. Sorry that one of these timescapes goes up and then the other one goes down. But this human modified river system then is quite complex in itself. So we've got levees being introduced and raised. We've got Gavin's Point Dam completed, the spillways completed as well. So the spillways are the management, and we'll talk about this a bit later, are the management of how the water is allowed to release into the floodplain, which is a strong deviation from these natural crevasse clay deposits that we're used to studying. The old river control structure as well is, I mentioned earlier that the river would like to be flowing towards Atchafalaya Bay. The old river control structure is kind of in place to manage the flow of the water that goes down to Atchafalaya Bay. As a lot, I think before that was installed, the river was starting to show signs that there was perhaps a preference for that route. So then we look into Atchafalaya Bay itself. We've got the Wax Lake here, and then we've got the Dredge Spoil Islands forming by 2015, where this artificial channel here has been carved, and we've got these beautiful deltas forming, actually creating new land down in Atchafalaya Bay. So if we look at the levees, then the natural stratigraphy of the internal architecture of some of these levees looks a bit like this. These are the models we're used to. We've got the flood stages, and then repeated flooding can cause these natural levees to build up, which becomes a natural flood defense for the river itself. When we look at the Mississippi levees, we've got almost concrete stratigraphy along some of these, and you'll notice that the maximum water level that the levees are capable of holding is quite a bit higher than the floodplain itself, which is possible through the natural system, but to this extent, it is something that is certainly novel to the Anthropocene. Another thing as well, trying to manage these rivers for safety purposes, and for the significant role that the Mississippi River plays in the economy and things like that, and trade routes, is really important to manage this river. And one of the things they do is, as well as mat sinking, so they will place concrete mats onto the bottom of the river to try to help with some of that management. So when we think about channel confinement, the freely meandering and confined channel has now been artificially confined due to this anthropogenic influence. So the river has become isolated from the floodplain, hence changing the hydrology across the landscape and increasing the rate of some local subsidence because of the lack of water flow. We find the point bar deposit that would be related to the channel is not as deep as the channel itself, as this has been deepened. I think it's something like a figure that I heard was something like an extra foot of depth in the river is an extra $1 million of cargo that the barge can carry. there's a lot of motivation for that. So yeah, what the most interesting thing I find about this sedimentologically though is that this kind of situation used to be only in bedrock systems on land in terrestrial settings, and now because of human influence we are seeing fluvial channel confinement where the channel is isolated from the floodplains and they are no longer in equilibrium along many systems that used to be freely meandering. So because of this, I started to think, well, we need new geological models. And, you know, the things that we are using to try to understand these systems is no longer working. And as the Mississippi River has been dubbed as the Anthropocene River, I went to an event there, the Anthropocene Campus, which was organized through the Anthropocene curriculum. And yeah, you just kind of start seeing that a lot of the sedimentology isn't working in the way that we might expect it to. First off, you know, the main thing is a natural system, and the ones which would have been occurring while Fisk maps were whilst the morphology that we see in the Fisk maps was developing, that was something that we'd call a meandering system, because meandering is the verb, that is the active word, that is the river actually actively changing shape. What we now see could perhaps be described as more sinuous, because it's a sinuous shape, but it is no longer meandering. And seeing as the Mississippi River has been at the center of many of these original descriptions, it is the classic Birdfoot Delta, it is the classic meandering river of the world. You know, it makes sense that, you know, let's begin with the Mississippi and make it the classic Anthropocene River too. So we're seeing a lot of changes to this, and you know, we're seeing subsidence here that is caused by oil and gas and extractive things, leading to subsidence of the ground, and then that is then taken to petrochemical factories, which is causing carbon dioxide and then sea level rise. So we're seeing lots and lots of things. This is designed to mimic the Bonnet-Carré spillway, which is just up from New Orleans on the river. And the spillway is opened when the river is too high to try to help to manage it and protect the city. So you see that, you know, what used to be a river that could flood all the time, I think there used to be overlapping crevasse clay deposits along the sides of the river, is now very, very managed. You know, this is very different to the models that we've seen before. So when we're looking at river systems today, we find that they are profoundly different from the ancient record. We have changed the morphology, the grain size, lithological composition, the grain, clast and grain characteristics, juxtaposition of strata, the lateral and vertical variability, and paleoflow indicators, and biological influence. So the geological record, as we would recognize it by current models, is being shredded by anthropogenic impacts. We don't really know what the scale of impact on rivers in the future geological record will be, and so anthropogenic alteration ought to be included in new geological models. Now, the diversity of rivers today is higher morphologically and functionally. The diversity of morphology and function is much higher than it ever has been in all of Earth's history. So, you know, if your friend says to you, "Oh, meet me down at the river or something, I'll see you in like in half an hour or something," you really have no idea what you're looking for, whether it's going to be sort of a flow of water in a concrete corset or something that's quite natural surrounded by trees. We really have no idea what we're looking for, because the word river means so many different things. So this, again, will be out in the next couple of months. We have natural systems or wild systems, which is the Holocene related system. We have managed systems where, you know, the river can still flood of its own accord, but it's kind of, you know, managed as to where that can happen to protect civilizations. And it might be dredged to help for shipping. And then there's modified channels, which, you know, is sort of like the Mississippi River, where we've got the original path of the river, although maybe we've had some artificial cutoffs, but we have, like, you know, changes and the river itself has been modified, but the flow of water is in the same position. Then we have transposed rivers, which is where the river itself has in fact been moved to either underground or somewhere else to make way for urban development. So yeah, there were another couple as well but yeah, you'll see in the paper when it comes out soon. So novel processes then. So we're going to scale down now. We've had a look at the landscapes and the models, and we're going to scale down and have a look at novel processes. So pollution, abundant plastic pollution and other anthropogenic litter impacts ecosystems, which gets transported to the ocean. And as we're reducing overall the amount of natural sediment that we have in river systems, perhaps because of being trapped behind dams and things like that, we are seeing an increase in anthropogenic material. So these two things are proportionally decreasing and increasing. Microplastic concentrations are seen to be quite high around wastewater treatment plants. This is an excellent paper. I encourage you to go find it if you don't know of it. And there's an awful lot of trying to figure out where all these materials are coming from to understand the source to sink profiles of plastics and understanding how they travel. Microplastics through fluvial systems as well is really important. Trying to understand how they are input, transported, remobilized, and stored to try to mitigate, the understanding for cleanup operations. As it's rooted, we're seeing things like food packaging moving in suspension and clothing and stationery being caught up in ballistic impacts or something. And then we're looking at microplastics, and they can be ingested by biota, and all sorts of things can happen. But what you'll notice in both of these diagrams is that the bed load here, the actual bottom of the river, aside from a little bit of burial over here, is mostly empty of plastics. And I drew this diagram, so this is my fault too. So if you're having a look at sort of this, it just sort of doesn't make sense from what we know about sediment, so I decided to investigate this. So the aim of this study was to determine if plastic affects riverbed forms. So we know how we have the erosion of material on the back of the dune, on the stuff side of the dune, and then deposition of the material on the lee side of the dune in the recirculation zone. And then over time, this repeated process causes the dune to migrate downstream. This is a quick video of before we polluted these poor sand dunes. So we put 1,200 kilograms of sand into the recirculating flume tank at Hull University, 10 centimeters deep sand deposit on the bottom, 20 centimeters of water above that. Put it up to about 0.5 meter per second, and then added about 1.5 kilograms of plastic, which was really, really not very much by mass. And then we temporarily increased the discharge for 2 hours to simulate flood conditions and promote the plastics in the sand to mix. And the plastics we put in, there were polyester cotton, fleece, and wet wipes, all cut to 1 centimeter by 1 centimeter squares, some fleece fibers, some PVC powder, a selection of Mardi Gras beads, thermosetting plastic fragments, some cigarette filter tips, pony beads, BB gun pellets, and 4mm beads as well. And these are the properties of each of these, but I'm just showing you this for the bits selected in green. So we noticed overall that their mobility was high or low through the experiments. And we decided to focus around the RD value for understanding the mobility. So the RD value is the equivalent sphere diameter, So all of these are made of the same thing, so their density is the same, but their diameters are different for the Mardi Gras beads. So, but their submerged specific gravity is the same. But if we multiply the diameter by the R value, then we end up with their RD value, and that's the bit that we have studied. And we noticed that the change in behavior from high to low mobility changed around about 1.6. So between the BB gun pellets and 7mm Mardi Gras beads. So the RD value of change at this speed with these materials of this shape is about 1.6. So now we're going to have a look at how some of this happened. So for the low mobility particles, if we have an individual particle resting on the lee slope, we're seeing that it will just simply come to rest in the recirculation zone and then become buried. If we're looking at a low mobility plastic group, we can find that we have, a selection of high density plastics, and you can see this low density, high mobility bit of polyester cotton here that becomes buried by a bit of sand, and then it can be weighted down and kept into the deposit. And overall, this just simply becomes built over as the sand will avalanche and bury that deposit overall. But most of the materials that are sitting here, we know are low mobility. So how do we track the high mobility? So we coined it multi-layer deposition, and you can see this little layer here of pony beads. And over the top of this, we've got a lot of other material, enough material to kind of buffer the turbulence of that recirculation zone such that when the sand creeps forward and the dune migrates, this layer here can in fact be buried. And we'll see that happen just here as the sand will avalanche down. Avalanche is a strong word, but you know what I mean. Comes down and covers them over. So in that way we can get the deposition. Now this kind of like grouping can persist for some time, and that can end up with a group deposit as a lens. So when we get this multi-layered deposition, we're getting repeated layers of this because we've got this high amount of plastic at the lee side. And bear in mind how little plastic we put in. You know, because it becomes accumulated in this zone, this can happen. And we have the deposition of individual particles as well, and we've seen most of this occur. So then we have erosion of filter tips. So just watch here on the Stoss slope, where this filter tip will ping out and we'll end up with this scour. So this dune is now having to recalibrate and figure out kind of how it's going to shape next. And what we can see in here is in fact a lens from there being an accumulation of plastic on the lee slope, which you see is now gone. This one will pop out as well. But what I should say is that, you know, I know that a lot of plastics and I know that dunes and things do change their shapes. We do know that this can happen, but this is a constant flow speed. We did not change the flow speed. The only thing in here that is causing this to happen and for there to be inconsistency is plastic, and the frequency at which this happened, filter tip's about to go, the frequency at which this happened is quite remarkable. So notice then the overall shape of this dune has now changed because of its recalibration. So the dune shape adjustment causes the sharp crest to become a rounded crest at a lower height with a lower sand volume. And we're seeing these individual particles become eroded because they have a low erosion threshold, and also the fact when they become exposed, as you'll see in the next video, that encourages scour to happen around those particles. Now we'll have a look at the group erosion. So this is where we get a lens removed. So this had already started by the time I found the video, and this video is in two parts. The first part is at the back of the dune, second part of this video is at the front of the dune and about 3 seconds later on. So you see we've got this lens here that's eroding, and when a particle becomes exposed, the scour can increase around it. Particle isn't always removed. The scour doesn't always get deep enough, but often it does, and it can be very rapid once that starts off. So yeah, we're seeing the removal of quite a few particles here, and you can see that the shape of the back of the dune is changing quite rapidly, and that will be causing the rest of the dune to try and re-equilibrate as well. So now the front of the dune, and you can see this steeper Stoss slope marching forward towards the crest. And yeah, this dune ended up becoming quite symmetrical. I think it survived, but it was much smaller in terms of sand. And all of this adjustment happened simply because of the inclusion of plastic. So it can lead to dune washout if this keeps on happening. So you can get the individual class kind of causing, you know, this to happen and for the dune to readjust itself. And then you can also get washout due to a group where we get the increased influx of sand, plastic and sand into suspension. And this can kind of cause the reorganization of, you know, the dune can then reorganize and then continue and become stable. Or if there is plastic in this front part of the dune, then it will continue to destabilize and actually be washed out. Yeah, and the videos that I've just shown you as well, those were still occurring the next day after running overnight. So trying to mix the plastics in doesn't always necessarily work because the plastics will sit on the surface as they are being more readily worked. So we find that plastic is not passive in fluvial systems. It needs to be included in diagrams. Plastic inclusion changes the ratio of suspended to bedload material, and the inclusion of plastic encourages river to develop more conduit-like properties, and then these heterogeneous deposits also. So if we think about how we're sampling rivers, for example, you might simply put down a Van Veen gravel or something and take whatever's on the surface, but actually your pollution would be underneath this, underneath the crest of the dune. So it's something we maybe need to think about moving forward. So when we think about this image that I showed you earlier, and we look at this again, we find that in fact, maybe we're seeing something a little bit different. here's New Orleans. This is the famous Belize Delta and all the amazing swamps, and the Bonacari Spillway is just up here a little bit, just off the bottom of this diagram, this photograph. So when we're looking at this, maybe we're seeing something a little bit different. Maybe we're no longer seeing a meandering river. Maybe we're seeing a sinuous system that is highly managed for the safety of the people who are living around it. But nevertheless, this is a new type of river that needs new models, and is setting the precedent for how we're going to, look at rivers around the world and how we're going to be managing them moving forwards as well. So to summarize, plastic is not a passive component of sedimentary systems. Humans have deeply affected the natural environment, including sedimentary systems and river systems through engineering and pollution and many other active and passive means. We do not yet understand what the long-term implications of these changes will be or what the sedimentary record is going to look like. So if we reconsider this a little bit, the scientific basis of sedimentology is uniform tonism, and what we talked about with that, what we're relating to what, and maybe we need to be a little bit more careful. Maybe there are certain things that we need to be taking a small step back on and thinking, well, has a human influenced this? And therefore, do we need a new way of approaching it? And where do we actually need to draw the line on what we can relate from this previous study to this other site? So future work then, the Anthropocene Sediment Network is an international interdisciplinary group that I set up in 2020. And we're kind of building this scientific knowledge network in a multidisciplinary sense, and then trying to adapt that work for education. Our website at the moment is a bit of a bit simple, but we've got quite a lot of stuff we're going to add to it in the next couple of weeks. And in the team, we're exploring ways in which novel sediment processes are working and seeking to understand the border landscape and all that kind of thing. So far, we have some funding from the UNESCO IGCP 732 fund. But yeah, we're looking, if you're interested in this kind of thing and there's something along here that's sort of tying in with what you're doing, just drop me a line, and yeah, I'll see, like, if you want to connect in or anything. So yeah, lots to do, but we understand that there's this is a new world, so why not? So thank you very much for listening. I have to take any questions.
Thank you very much, Catherine. So that's a wonderful talk, and give us such a good overview from the river basin, delta, and even plastics. Very good. So let's see the audience. If you have any question, please go ahead. You can unmute yourself, and you can go ahead directly ask Catherine. Anybody? Catherine, I see your experiment about the plastic particle, but those pretty large. I mean, in terms of the size, but there's many plastic is macro size. I mean, those is how impact the environment and the river sediment. Is any impact? How could we evaluate that, the influence of those smaller size of plastic particle carried by the river?
It's really hard to do that. So the study that I've just shown you is, as far as I know, the first study that has actually looked at the interactions between plastic and sand on a riverbed in that kind of setting where the plastic and the sediment is both moving. So it's kind of very, very beginning stages of figuring out what the truth is on all of that, how much of these things affecting us. We know that, macroplastics and things are easier to observe when they're floating. Not easy by any stretch, but like easier than what's underneath the water, because it's really hard to observe all of that without disturbing the processes. So yeah, we don't know yet. We'll figure it out.
That's interesting. And other thing is many impact of the human intervention we have kind of already emerged. We already know them. For example, sediment reduction. For example, the levee. For example, the subsidence or shoreline erosion, water quality deterioration. All is a known things, issues. is anything is not yet coming. Something will coming, some bad thing will coming, anything in your mind. We haven't seen really happen yet, but definitely will coming, something.
Yeah, I mean, I'd probably say it's the warmer and wetter weather that we're expecting with climate change. We'll find out, I guess. I don't know. I think it's really hard to, I think as with everything, you know, it is the accumulation of the effects rather than any one effect itself. So when we're sort of thinking about the diagram, say, for example, that I showed of the geological model of the Mississippi River, that is an accumulation of many, many things. Any one of those things probably wouldn't have, you know, caused us to say, oh, we need brand new models for rivers, but it's the accumulation of all of those elements coming together that kind of makes you think, hang on, this is now functionally different. Like sediment is moving completely differently across this. Like the sediment is being taken out of the floodplains and then put into buildings, just like, you know, it's kind of, it's crazy. It's just very, very different. So it's the accumulation of stuff, I'd say.
I have a question.
David, go ahead.
I'm just curious if when you do the experiments with the plastic, if you noticed the particles changing, are they changing in shape and abrading, or is there much going on with that when you interact them with the sand particles? Are they significantly affecting the shape of the plastics?
Yeah, so a few things happened with that, David. One of them, the 4mm beads fit quite snugly into the pony beads, which meant that some of the pony beads actually behaved much more differently than the other ones because they were more dense. So they were a bit of a pest. So we're trying to yeah, so that happened. As far as materials being abraded, pretty much all the paint came off the Mardi Gras beads that we put in by the time we got to the end of the run. Which is kind of a problem because you know, that paint has got lead in it and things, unfortunately, some of it anyway, and so, you know, that is potentially an environmental concern, but that's another problem, I suppose. So yeah, things did change shape. The fabric broke down pretty quickly and all got stuck in the filter, which was a lesson learned, and some of the filter tips, they frayed on both edges. So we ended up sort of with a slightly different shape that was frayed on each edge as well. And the wet white particles that we put in pretty quickly picked up as many fine particles as they could and then changed their density also. So there was a lot of really interesting interactions actually that we noticed with how all of that was going. And we learned an awful lot for the next experiments.
Yeah, okay. I would guess you might be forming a lot of the microparticles from that. Yes.
Yeah, we did collect some water actually, and it was quite alarming. I've got the data for that somewhere. Maybe I'll write it up one day.
Okay, thank you.
Anybody else? Catherine, I also very worry about the dams because as you mentioned, in the last 200 years, human built more than 50,000 dams across the world, but many of those dams begin to age, and the safety of these dams. First of all, you know, the function many of them is gradually lost, is reducing because sediment accumulation, you know, the volume reduced. Sometimes they lost the function to control flooding. And also the dam collapse is beginning to more and more. Like a couple of years ago, the thing happened, I can't remember, Laos or Cambodia, South Asia, caused so many people died. Yeah. So that's something catastrophic, you know, destructive impact could happen more and more in the near future. That's really.
Yeah, I mean, it's not nice to think about, but it's, you know, these flood events that would presumably have like large concrete blocks and things, you know, maybe this is something that it's really hard to know. It's really hard to know, but you're right that dams are changing. There are many of them. When the dams were actually installed, sea level didn't rise for a couple of years because of how much fresh water was being withheld. Like, humans have really impacted the hydrological cycle.
Yeah.
So I think that there's an awful lot that we can, learn from maybe studying some of that a little bit more, which I'm quite excited to get my teeth into, actually. Which reminds me, but anyway, I won't go into all of that now, but it's really, really interesting, and that they are losing their functionality, and to dredge them and to keep the functionality high, it's really cost intensive.
Yeah.
So yeah, it's really quite fascinating.
Yeah, particularly in a developing country and or economy poor country, that is media to small size of them, the safety is more concerned.
Yeah.
Okay, so anybody else?
I think Noor's asked a question in the chat.
There is one
Yeah,
in the
Clinton.
chat.
Go ahead.
Catherine, I think there is one in the chat.
Yeah,
Oh,
I'll answer
sorry, I
this.
didn't
So hi Noor, good to see you. Noor said, has asked, do you think a sedimentologist should accept that plastic is a different grain size material in sediments and could name the sediment after the 1980s? For example, sediments belong to plastic age. That's a really good question. I've actually just recently been reading this, which I highly recommend. It's a wonderful, wonderful book by Tracy Williams called Adrift, and it's about Lego that got spilt just off Cornwall in the UK. So that's south of the UK, and yeah, it's crazy how we define sediment. There may or may not be a paper coming out soon. The preprint we're hoping to release in June. So keep an eye out on the Anthropocene Sediment Network for that on my Twitter feed. There's a really good point, though. Yes, and we're working on it.
cool. That's nice.
Hi, I have a question.
Hi, Sarah.
Sarah, yeah.
Hello. I'm just curious in your opinion then, just based on your thinking about plastics and in rivers for this long, is it possible that some of our chemistry budgets for sediment fluxes and chemical fluxes in sediments are wrong because we didn't take into account the presence of plastics, if that makes sense?
Yeah, I mean, there's a lot to question here, and I think you almost know that you've done a good experiment when you come out with far more questions by an order of magnitude than you went in with. But it's kind of we scaling it up to have this kind of depending on the type of river that you're going for. We were trying to mimic small urban streams because a paper recently came out that said that they were the most polluted proportionally. So I think that because we have seen that there is an increase in the amount of sediment that goes downstream because of this plastic, yes, possibly there could be an extra consideration to make. Whether I would go so far as to say that it's inaccurate or anything like that, probably not. Like, I think it's just an increase in another error bar, I suppose, that maybe needs to be put in, and we're just still understanding the scope of it. It's all quite new. I wish I had more answers.
Thank you.
Thanks, Sarah.
So if no any other questions, so we can stop here. And Catherine, thank you again for your wonderful talk. This talk is also archived on the YouTube channel. So so hopefully I see you everybody next week. Okay, thank you.
Thanks, Paul.
Okay, bye-bye.